Hello, everyone. Thank you for coming to our talk, Don't Let Your Kubernetes Cluster Go Wild, Ensuring etcd Reliability. So if you're an end user or a direct customer of etcd, or indirectly using etcd as one of your Kubernetes distribution, this is the right place for you. So little about ourselves. I'm Arka Saha, a software engineer at VMware by Broadcom, currently contributing to etcd and also responsible for downstream releases of etcd and Kubernetes.
I'm Henry. I'm a software engineer at Google, and I also contribute to etcd.
So before we start, we would like to extend our sincere thanks to Benjamin and Marek for laying the foundation and maintaining the etcd and its testing framework, as well as supporting this talk with their invaluable knowledge. So in this session, we will introduce what a distributed key value store is, the design principles of the robustness test and the deep dive of it. And finally, we are going to demo on how to run a robustness test. A good reference of handling the data inconsistencies in etcd via robustness test framework has been covered by Marek around 2 years ago when it was designed and implemented. You can refer to that. Also, if you are looking for a beginner-friendly primer of what robustness test is and how you can use it too, you can refer to our talk from last year in OSS Japan. With that, over to Henry for more about etcd and its constraints.
So let's have a quick intro on distributed key value store. So etcd ensures strict serializability, but what does that actually mean? So let's take a step back and think about what correctness actually is. So let's say we have two operations. We have put a equals to 2, and we have a get a out of the key value store, and we execute them sequentially. So intuitively, we would expect that the get result would be the value that we did the put with, the last one that we put in. So that's how intuitively we think of how the value will be getting out of the key value store, right? But if the requests are actually overlapping, like when they're being executed concurrently, how would you define the correctness? So before that, let's discuss the representation that we'll be using throughout the slide deck on how we represent the operation history. So on the left, you can see that we have clients, 0 and 1. So we have two clients in this graph. And each of the clients, they can only execute one thing at a time. So if there's a request in flight, we cannot send another request for that very client in the same time. And for each of the rectangular box, on the left edge, it's the time that the client sent out the request. On the right edge, it's actually the time that a response is received for that client. And the blue line is the instance that the operation is applied. So coming back to the question, so what if the requests happen concurrently? For example, consider above case where we have one put request and two get requests running concurrently. As you can see, interestingly, client 1, get A, actually returned result 1. Get client 2 actually had the result 2. So is this a valid case? Depending on the consistency model, we can have different answers. But in etcd's case, because we're using strict serializability, this means that the operation appeared to have occurred in some order consistent with the real-time ordering of those operations. So in a sense, coming back to the example before, it means that if we can find a set of linearization points for all the operations, then we can say that the operations are correct under the consistency model that we're using. So in this case, if we actually do it, if we assign the points that we have client 1's get A goes through first, then client 0's put goes through, and client 2's get goes through, then this is a valid history. So let's hand it back to Arka and see how actually etcd work under this model.
Thanks, Henry. So here we have a diagram that illustrates an etcd cluster consists of 3 members, 3 clients, making concurrent requests to each of those members. As we see, client 0 has made a put request, and even before the response is received, client 1 has made a get request. As Henry mentioned before, this is a typical case of overlapping requests, and we can also refer to the timeline graph on the top right-hand side. So what we see is that the request of client 1 overlaps with the request of client 0, and the client 2 overlaps with the request of client 1. But at any point of time, we see that the response of the request from client 0 has been completed before the requests from client 1 and 2 are executed, which is like demarcated by the blue line representing the logical instance of time when it was actually applied to the system. And thus we see both client 1 and client 2 get the correct value with the updated value of A and the most updated revision. In an alternate scenario, we can say, see the client 0 make the same put request, and it gets completed almost instantly. So the response of OK revision equal to 5 is received at that instant. In this scenario, if client 1 makes a request, get request, and it has been completed, and already client 0 has seen the value of A equal to 2, client 1 cannot see the value of A as 1. And that's what is happening here, which is what is breaking the system, and that is what we want to avoid. As a general rule of thumb, the revision should only increment, and at any point of time, the current revision should never be less than the previous revision. And in this case, the client 1 is seeing a previous revision or a stale revision, which means it's traveling back in time, and that's not allowed. With the problem of the revision going back in time, there can be real-world problems like network connection errors. The network between the nodes can go down. And even in that scenario, the system should not respond with a stale data, and instead it should catch up with the latest data that is available on the other nodes when the connection is reestablished. Like that, there can be disk problems, either slowness or corruption of the disk, but as long as the majority of the nodes are active, the consistency of the system needs to be maintained. And there are a whole bunch of other failures like this, like packet loss, clock drift, upgrade, downgrade errors, and so on. And these can happen intermittently at any point of time, which is not in our control. And the nature of these failures being random and intermittent makes it more difficult to test, let alone testing it again and again every time with every commit. So in order to have a framework which can reliably reproduce such scenarios, such intermittent scenarios, over and over again with each and every commit that goes into a release, the robustness test framework was introduced. With this framework, we ensure that each of these failures that has happened in the past can be reproduced reliably, and it is fixed properly and ensured that in the coming releases, it doesn't cause any regression. So let's quickly see how the robustness tests differ from traditional tests like unit tests and integration tests or fuzzing. So the input for the unit and integration test is fixed. We know what the input should be. And for fuzzing, it is random, and it can be garbage values just to see the whether the system can hold under such scenarios. But for robustness test, it is random, but those inputs are valid. And while unit and integration tests and fuzz tests target the function, the robustness test actually targets the binary and the entire infrastructure stack. And the output is basically, for unit and integration tests, it's predictable. It is easy to assert whether it is matching or not matching. For fuzzing, we know whether at any given random value the function is failing or not. So that's what we need to check. But for robustness test, it's a little bit different, because we need to validate the random input that was given, and that's where the challenge becomes. And for the environment, basically unit tests, fuzz tests, and integration tests are all run as processes. But since for robustness tests, we need to have the scenario recreated, reproducible, we actually use as a process, container, as well as virtual machines. And using these robustness test framework, we have been able to uncover these issues over a period of last 2 years. And if we see these discovered by column, we get to see these have been reported by users and Robustness framework itself. And based on the necessity of these issues, they have been reliably reproduced, tested against each and every commit that goes into a release, and that becomes a very big part of the etcd data inconsistency effort that the entire team has put into for each of the release so that it can be stable. Over to Henry for the design principles.
Thanks, Arka. So let's dive into the robustness test. So here are the goals that we have in mind when we design the test. We want it to be able to explore. So it's kind of like cover the edge cases that requires race condition to manifest. And we would like to explore some code paths that's not covered by the existing unit tests and end-to-end tests yet. And reproduction, as mentioned, that we want to have an easy way to debug issues and ensuring historic issues that's not surfacing again. And validation, because now we are giving random valid input. We need to somehow validate the output. We want to also ensure not just the final state is correct, we want to ensure the intermediate state are correct, because we have the strict serializability promised in our documentation. So there are two main areas that we'll be focusing on for checking the correctness. One of them is the key value API. It should be strict serializable. It should be atomic, durable. And for watches, it's the order, unique, reliable. So it's like you cannot afford to have a missing watch event. And one of the main direction of our test is to make sure that we are as reliable as Kubernetes would expect us to be. So we set foot by understanding how etcd is used by Kubernetes, which is documented in this contract. We codify the interface, we test it continuously, so when we know that for the new bug fixes or new features when we introduce it, we won't break Kubernetes by accident. So let's talk about the execution stages of this test. So there are three main stages. There are setup, execution, validation. So for setup, we will cover the configuration, and we will be configuring the scenarios. For execution, we will generate traffic from clients, we'll inject error, and we will collect the output from both client and server. For validation, we'll run it through the checker and see if we detect any anomaly. So let's go one by one. For the setup, we need to set up the cluster. And to set up a cluster, we start it from a clean state, so it's an empty database. We start the etcd binary, and we will configure a number of nodes, node versions, and the address so they can communicate, etc. And for scenario, we have, as mentioned, exploratory or reproduction. For exploratory ones, we will configure things like traffic profile, different leader election timeouts, or different snapshot counts. And for production scenarios, remember this table that we mentioned? We would like to reproduce some of these scenarios that requires race condition or failure injection to actually occur. So let's take this example where it requires this wrap before save panic fail point to reproduce the error. So we will have to specify what fail point, under what profile and traffic. It will be a very efficient way for us to reproduce, so we can cover this in the future CI runs. So having done the setup part, we have to execute. So to execute, we have the client that will generate requests and send it to the server. And the requests are defined in the scenario. And so one example of the defined configuration might be the traffic. And for traffic, you can see this is one case of the traffic where we have different combination of the requests that will be sent. And during execution, as we also have mentioned, we will have to inject failures. The bolded ones are the ones that we currently have the test is able to inject. And how do we actually do that? We will have to rely on three different frameworks. Well, not frameworks, but tools. So we have GoFail, we have LazyFS, and we have the network proxy. So let's go one by one. The first one is GoFail. It's a project under the etcd organization. So it enables us during runtime to inject failures into certain code paths. And it's very simple to use. So as you can see, in the function, you can comment with GoFail, and then with the certain format that you follow, then you can use GoFail to generate the Go code from the comment for you, and then you can compile this code with this GoFail code contained inside, And during execution, you can use HTTP endpoint to enable it, or use environmental variable to enable it on start. In our etcd codebase, for example, we have this panic code here to interrupt the leader to send out messages in the RAF part of the codebase. And if we enable this during the test, then the node will crash, and we want to check in the end the cluster is still in the consistency order that we are expecting it to be. The second tool that we mentioned is the LazyFS, which is what we use for testing the storage, where it can simulate data loss or unsynced writes. And lastly, for the network, we had the reverse proxy basically sits there and blocks off traffic when we ask it to, so it can simulate some sort of network partition or partial network disconnection. So we have talked about generating the request. We have talked about injecting failures. Now we talk about collecting the output. Since it's a client-server architecture, we have to collect from both sides. Server side, it's basically we collect the write-ahead log from the server and also the snapshots. The client side, we will record the requests and responses, and we also record the watch responses that we have streamed continuously. And what do we actually record on the client side? It will look something like this. Let's break it down. So basically, we record the client ID, input, which is the request payload, the request time, response payload, and response time. And in case of error, we record that too. And as we have seen in the previous slides before, this is how we can represent it. So for each client, you can lay out the events in this visualization. And we will have to run the validation basically on this. So recall that we said we generate random valid input. It's not like unit tests where you already have the input and output hard-coded. So now we need to figure out a way to verify what the output is correct or not. And to do this, we have to use a state machine. So just a quick refresher, state machine, you will start with some state, in this case, a equals to 1. And each of the operation basically is a transition from state to state. So if you put b equals to 2 into the system, it will then go to the state where you have a equals to 1 and b equals to 2, and so on and so forth. So using the state machine, you can verify all the intermediate steps, and you can also verify the final state if the etcd cluster is in the correct working order. So when we're modeling etcd using state machine, the idea is that we have a simplified implementation. We don't have wraps, we don't write to disk, we just in-memory hash map basically, because that's basically what key value store is. So now, having modeled this, given a history, we can then walk through the states and verify if the etcd is actually in the correct order. So having built the etcd model, we then leverage Porcupine to help us. It's a fast linearizability checker. So coming back to the visualization before, what Porcupine will do is it will assign linearization points throughout the history. And if you follow this visualization, you can actually follow the lines, and you can see your system state evolves over time. And in this case, it's correct because it doesn't have any red line. So we're all good. There are other type of validation that we also build into this test when it's running, because it's targeted for STD. So it's like we can check some internal consistency, like at the end of the test we can check for the hash KV, or we can also check if the successful operation observed on the client side is actually also presented on the write-ahead log side. So in the unfortunate event that if we actually get a report like this, where you can see we put a key and we have a revision 165, somehow the future get actually have a revision 164. This time traveling backwards, not good. This is an example that we have showed earlier in the slide too. What can we do about this? So hopefully we don't need to do this a lot of times, but yeah, if ever we have to run the report locally. We have to first actually make sure if this is actually a real bug on the etcd side, because as we mentioned, we are writing a model to model the behavioral etcd. So there might also be a case where there's a bug in the framework, there's a bug in the model. So we need to actually first distinguish this first. And then if we actually know this is a bug on etcd side, try to reproduce it over there, fix the bug, write end-to-end test. And for those that actually require race condition or error injection to work, we add it to the Robustness test suite so we can consistently reproduce it over time. So let's do a small demo. This is basically demonstrating the issue that we have. As we mentioned, the the revision travels back in time. So since all the test cases are written in the makefile, you can just run make, and that issue number, and it can actually reproduce the bug. And what we're looking at is what we have recorded on the client side has operation and watch, and we also have the server side, we have the snapshot and the write-ahead log. So we can quickly take a look at what we have stored for the watches. It's basically the events that's observed on the client side, the put and delete operations. That's basically we have it logged structurally. And then we can take a look at the operation side, what we log over there. It's basically also following the structure that I presented in the slide earlier. Every client will, if they have, it can have both. It can also just have the watch and also just have the operation. Then we will show, basically that's what we recorded, and the robustness test will always generate a report if it fails. And you can, that's where usually when we're debugging it, we will look at that report and trying to figure out at which point the history starts to violate the property, the consistency model property that we're trying to see. So this is, when you open the report, this is what you would see. You can jump to the first arrow to go straight to it, or you can enjoy scrolling and try to find where the red line is. And yeah, this is where we showed in the slide. Revision 165 goes backward. In the future, in the future, it goes backward somehow. So yeah, this is the bug that we discovered with this test suite. So some future work, starting I think next week, we will have this antithesis integration thing. We will explore new ways to reproduce our bugs consistently. We will try to see how antithesis can help us improve our robustness test suite. There are a lot of GitHub issues that's open targeting the robustness test, something like adding more internal consistency checks or deflate CI runs, like we have the long-standing issue of QPS. And also, we run bi-weekly robustness test meeting where we look at this beautiful dashboard. This is all green, so that's good. If there's a red or purple, that means there's something that failed. We need to look into it. And can join us for a ride to bi-weekly surprise, because we really don't know what we will see every 2 weeks. So yeah, thank you for listening, and hope you enjoy this talk. And yeah, have a nice afternoon.
Hey, thanks for the talk. So it seems like in the robustness test, you're kind of relying a little bit on non-determinism, right? Like it seems like the requests that you're simulating are random weights and probably running in random order. Do you run these tests numerous times every time you run them? And look, how do you make sure?
Yes. So for reproducing the issue, if you actually check the makefile, we usually have a count for like 100 or 200, depending on how hard it is to actually reproduce it. So it's not like one shot you get it. Like the example we show is actually kind of lucky. For some tests, you actually need to run several hundred times, and because it's race conditions sometimes to trigger it, right? So this is kind of why it's hard to, like debugging this criticism is hard because of this.
Has there been any interest in like using more formal proof verification tools, or like I'm not gonna say TLA plus?
Yes. So on the RAF side, there's actually work on the TLA plus. There's a work on that. But on the etcd side, I think there were a pull request open, or there was someone trying to work on it, but it hasn't really been worked on like within.
Yeah, I think maybe like less formal proof, but more like frameworks like Jepsen, Maelstrom, those kind of tools. Probably more pragmatic, right?
We did have Jepsen test report. If you actually look at it, I think on 3.4 they actually ran it once. And the problem was that on Merrick's talk, he actually mentioned it. So the way the test is designed is not really able to run on CI. You actually have to set up a cluster of servers, and also. you need to really have some very deep knowledge into how to write them, because it's not like by magic it runs. You still have to write a model and whatnot. So for us, our expertise is in Golang. So we decided to write this test ourselves. We do this framework. We do the same check, and we can do more internal consistency check and whatnot to run this on CI, and also for us easier to track and debug.
Yeah, makes sense. Thank you.
You can talk to Merrick if you have more questions. If no question, then thank you everyone for attending, and have a nice weekend.
Thank you.